Can everyone see my main screen? Bronwyn, can you see that? Excellent.
Yep, we're all
Perfect.
good.
Excellent. Well, thank you very much for having me and that really kind introduction. Yeah, I've been in Bristol back in the UK, which is sort of originally my home for about a month now. And I'd lived in Baltimore and Canada for about 8 years. So I'm readjusting to life in Britain, but it's going okay. But I miss Maryland and the East Coast very dearly. So I'm really happy to be talking about it tonight. And so as you'll see, and as you've probably read, as you've come to this talk, I'm going to be talking a little bit about garnets, this mineral from Maryland, and how these minerals might tell us something about the formation of the Appalachians. And I sort of like this sort of bit at the front of my title, which says, not all rocks are created equal. And that's kind of a little joke between different kinds of petrologists. So igneous petrologists who study rocks that come out of volcanoes, and sedimentary geologists who look at things like sediments and muds that have been deposited, and metamorphic petrologists like myself who look at those other rocks that have been cooked up and churned into mountain belts. And so I'm very biased, and I think the rocks that I look at are by far some of the coolest. And so I'm going to be talking about, like I said, some of these Maryland garnets, but I should say right off the bat that all of the things that I'll be talking about and the concepts that I'm going to be discussing have been done in conjunction with colleagues of mine at Johns Hopkins, Daniel Viette, who was my postdoc advisor, and some colleagues of mine at Boston College who were instrumental in some of the research that I'll be talking about towards the later half of the talk. And I'll move forward if that works. Has the slide moved forward? Perfect. Okay, we're in business. Okay, so diving straight in, what I'm going to try and do is answer a few pretty simple questions over the duration of this talk. And so ultimately, what I want you to take away from the next hour or so is not only how the sorts of things that rocks like this one here can tell us about the formation of the Appalachians and how we can use it to understand the geology of Baltimore and Baltimore County, but also the sorts of information that rocks like this, garnet in particular, within that rock can contain wherever this rock might be found in the world. So this kind of rock and the minerals within it are not unique to the part of Maryland that I'll be talking about. Maybe you'll be wandering around in some other part of the United States or abroad in the future, and you might think, hey, I think I know something about those little minerals. I wonder what story they might tell. And so I'm going to spend quite a bit of time thinking about these first 2 points. Why is rock metamorphism? And we'll define that in a second. Unique on Earth. Why is it distinct? And what does this mineral garnet tell us about these processes? And so I think it's important to place emphasis on this. It's sort of some fundamental geological concepts. And apologies if some of it's known to some of the people in this group. But I would encourage you to add questions to the chat. I'll be pausing periodically to answer any questions that you might have. I'm going to try and reduce the jargon, but I might slip here and there. So if there's a word that I say that you don't understand, please just shout, let me know. My sort of slightly sleep-deprived brain at this point is trying to catch up with the sorts of things that I'm saying. So I apologize if I go slightly ahead of myself, but please let me know. And so before we start talking about garnet and metamorphic rocks, we need to understand why they're so special, what they are and how they come to be. And so I've just talked about how I'm going to talk about minerals and mountain belts, but I actually want to start really, really zoomed out because I think this highlights the importance of the processes I'll be talking about in this talk. And so here we have images of the planet Venus and our planet Earth. And so Venus is the sister planet to Earth. It's a similar position relative to the sun. It's in this what we call a habitable zone. It's made out of pretty similar stuff. But the difference is between these two planets is that while Venus has developed this sort of thick and really stagnant stationary outer layer or its crust, the Earth has active plate tectonics, and we'll talk about plate tectonics in a second. They have active plate tectonics that basically means that our surface of our planet is really mobile over millions and billions of years of geological history. And so that mobility of our continents and of our oceans allows the circulation of gases and volatiles at our surface into our deep Earth. And it's not really understood how they regulate this, but the uniqueness of our life-sustaining atmosphere and the presence of plate tectonics on our planet is not considered a coincidence. They're thought to be really intimately interlinked. And so staying on this tract of plate tectonics, you probably all have heard at some point that our planet is divided up into a series of tectonic plates. And so this is what they look like in the present day. And so the important thing to know is that these boundaries, which I've marked on these lines here, some of them are spreading apart. So where I've got these arrows diverging, basically we've got two plates, two entities moving apart from each other. And so our planet is pretty much a fixed surface area, almost a sphere. And so you can't be opening something in one place without then removing or closing something in somewhere else. And so that's what we have in these red lines here. We have convergent margins. So basically we have divergence along these white regions where we're pulling apart, and we have things coming back together where we have these red lines. And so that concept basically led to the development of a really fundamental geological concept known as the Wilson cycle. And so this was a theory that was developed by someone called Tuzo Wilson from the University of Toronto. And so some of you might be familiar with sort of the theory of continental drift. And this is kind of the extension of that theory. It describes the motion of our continents and the cycling of tectonic plates, all of which makes up this sort of quite shallow, quite thin outer layer of our planet. And so what we've got here on the left here is a cross section of the crust. It's just a single snapshot in time. So here we have a continental plate, which is basically what you're all sitting on now, what I'm sitting on here over in the UK. And these dark regions are black oceanic crust. And so fundamentally, and as you can see illustrated in this figure, the continents and the oceans are kind of made up of fundamentally different stuff. And so in the initial stage of this Wilson cycle, as we call it, or the embryonic stage, is sort of when we get the very first breakup of a continent. So you can imagine we have this really, really big landmass. For some reason, we get some heat input at the base of that, and you start to weaken this continent. You start to cook things up, you start to sort of expand it a little bit, and eventually you get sort of flexing of that big continental landmass, and it sort of starts to pull apart a little bit, and it forms these long linear valleys like we see in the present day in the Afar Rift Valley in Ethiopia. So if you went to Google Earth and looked at Ethiopia, you would see the very early stages of a continent starting to pull apart. Eventually, we create so much weakness in the continental crust that it actually begins to break apart. And so we've got a gap in between here where our continent used to be. And so hot magma or lava basically comes up from deep in the earth to fill the space that's left in between. And we produce new oceanic crust to fill that gap. We don't produce new continental crust. And so once this process sort of starts, it's kind of self-sustaining. And so more and more oceanic crust is produced in this region that basically keeps filling in that space, which means that these two pieces of continents that used to be together sort of start to drift apart. And that's where we get this idea of continental drift. You get migration of different continents away from each other. And so what we see when this process happens, we form these really narrow oceans. And so actually the Red Sea is a really great example of this. We have these really symmetric coastlines and a very narrow little ocean. And you can kind of envisage, even just from this image here, how we might have basically just torn that landmass in half. And so this process basically continues, this spreading process, and we start to develop these really wide symmetrical oceans. And so a really good example of this is the Atlantic Ocean. We've probably all heard about the Mid-Atlantic Ridge. And so what we've got here is basically a bathymetric map of the depth of the oceans and obviously the elevation on the continents in the continents' case. And what you can see is that at the margins of these continents, and again, we've got this symmetry on either side of our continents, we've got sort of shallow regions where we're washing off lots of sediments and muds from the continents, and it's sort of settling at the margins of these continents. But then in the middle of this ocean, we've got this ridge, which is basically this point here, where we're producing more and more oceanic crust. As I mentioned, you can kind of see in this schematic that our continents and our oceans are fundamentally different. They're made up of different minerals, they have a different chemical composition. And so they behave in really different ways. And so as oceanic crust is produced at this ridge in the middle, it's really hot. It's magmatic rock that solidifies quite quickly as it gets into the water, but it's still relatively hot, which means it's quite buoyant as well. And as it cools, it gets more and more and more dense. And so at some critical point, basically, oceanic crust is so dense that a process called subduction is initiated at basically the contact between a continent and the ocean. And this is where our oceanic crust, like the Atlantic, for example, would get pushed beneath the continent. And so basically when we start this process of subduction, this burial of oceanic plate back into the planet, we start to consume our oceans again. They're buried deep under the continents. And so this is exactly what's happening in the Pacific. We don't have any active spreading, no new creation of oceanic crust in the Pacific, but this ocean is basically in decline. It's being consumed as subduction, which is this process here, happens all along the margins of this ocean. And so some of you perhaps were at a talk, I think probably over a year ago, by my colleague and great friend, George Geis, and he studies the sorts of rocks that are produced in this kinds of setting that are overlying. He studies igneous rocks that form when you bury an oceanic plate, you put in lots of water and lots of sediment and a lot of junk back into the earth. And it says, I don't want to be in there. I'm going to come right back out the top in a volcano. And so not only do we get lots of igneous activity and volcanoes along this ring of fire, as it's known, we also get massive earthquakes because we've got so much friction building up at this region. And so as this closure process continues, we kind of eat up the whole ocean. So this continent here has moved towards the left of your screen, and it's basically eaten up this whole ridge. We've lost that. And we get these really complex sort of narrow oceans, like the sorts of things that we see in the Mediterranean Sea. The tectonics in this region are super, super complicated because we've got really complex histories of closures of ocean basins in this region. Eventually, on the bottom here of the right-hand side of your screen, that ocean will close completely. And so these two continental plates that are basically buoyant and sitting nice and high on top of everything, they will collide. And we get this process called Aurogenesis, or basically mountain building. And so this is exactly what's happening in the modern day Himalayas. And so the Himalayas are rising at a rate of about a couple of centimeters every year, quite quickly. When you think about, over a few years, you're starting to get feet of rise of mountains. But the Indian subcontinent basically used to be down by Madagascar, and it got pulled off through this whole process, and it sort of migrated northwards, and then it collided with Asia, where it is now, and it's really just ramping up, and we're still getting this process of collision happening in this region. And so, move forward. I think this is where things get quite interesting. And so the crucial component of all of this, as I've said, is that in these really big oceans that we have, and I've obscured quite a bit of it here, we form sedimentary rock. We deposit sediments on the shelves of these oceans. We think we go off of our continents, we don't suddenly go into the deep ocean. We have sort of a gradient from shallow to progressively deeper. And through that region, we have deposited all sorts of muds and sands and calcite and carbonates and various body fossils and all sorts of junk just washes off the continent and settles there. And so this is the sort of example of the sort of thing we might expect to see along the margin of North America, for example, just pretty, as I would say, boring sedimentary rocks. And lots of my colleagues would not be happy about me saying this, but I am very biased. So we have these sedimentary rocks. They're deposited at essentially 0 degrees centigrade or 0 degrees Fahrenheit and 0 pressure. They're deposited at the surface of our planet, in essence. And so this on the left here is a plot that people like me, petrologists, use quite a lot. And here we've got depth increasing on the y-axis, and we have temperature increasing on the x-axis. And don't worry about all of these different colored fields here. Basically, we get hotter as we go across, and we get deeper and higher pressure as we go down. And so our sedimentary rock sits right at the surface. And so as the Wilson cycle proceeds, that cycle of movement of tectonic plates and opening and closing consumption of ocean basins proceeds, the sediments that sit at the margins of these continents basically get incorporated into this big old mess that is a continental collision. And so the rocks that were once sitting at the surface are then brought to really, really high temperatures and into really deep pressures somewhere deep within this mountain belt. And that in that setting, this mud is transformed into a metamorphic rock, this beautiful metamorphic rock that I'm showing here, for example, which is a rock from Ontario that has a mineral called staurolite in it. And so these kinds of rocks are diagnostic because they've undergone this process of metamorphism, which most broadly is defined as a process that changes the mineralogy, so the minerals within a rock, and the structure or the organization of that pre-existing rock into new forms, so new minerals and new structures, because of changes in the temperature and the pressure, or either of them. And so this is the process that happens at these margins. And so I showed you staurolite in that picture just on your screens here, these beautiful prismatic crystals here. But depending on the temperature at which rocks form at, and they can form all the way up to about 800 degrees centigrade, deep in these settings until they start melting at about these kinds of temperatures, different metamorphic minerals will form at different temperature conditions. So at low temperature, we have this really soft green mineral called chlorite. As we start to get slightly higher temperatures, we get this really beautiful mica mineral called muscovite, which is what makes up eyeshadow, for example, and what's in the silvery regions in this figure here. And then we see biotite, and I'll show you some examples of that in a minute, this brown mineral. And then we get into about 500 degrees centigrade, and we start to crystallize my favorite mineral, which is garnet. And so garnet is stable all the way up until 800 degrees centigrade, at which point we melt our rock. And so this index sequence is really, really important for trying to understand how different regions of rock and different regions of rocks that are exposed at the surface basically record different temperatures that allow us to reconstruct the sorts of things that happen in our mountain belt at the final stage of our Wilson cycle. And so hopefully you have a little bit of an idea about the first answer to this question. So why is metamorphism unique on Earth? Our planet is the only planet with modern active plate tectonics that move horizontally on our surface. And so as far as we're aware, it's the only place that happens. And that's the only way we can get really shallow surface rocks really, really deep into our planet. Okay, are there any, before I move on, are there any questions that have come up from that very quick whistle-stop tour through the whole history of geology?
Any questions?
Oh, the chat.
I don't see any in the chat right now.
Perfect. Okay.
Great explanation.
Good stuff. Okay. So we've kind of talked a little bit about opening and closing of oceans, how this mineral garnet might be involved in that whole process. But I want to talk now about what garnet can specifically tell us about these processes. If I went into the field and I found a garnet, what might that be able to tell us about how old these mountains are, or how hot they got, or something about the evolution of our planet? And so most people think about this mineral garnet. This is what they tend to think about. So these are some examples of some really beautiful gem quality specimens of a variety of types of garnet. And so garnet has a chemical formula that contains things like iron and magnesium and calcium and manganese, some aluminium and silica and oxygen. And so it's all bound up in this crystal lattice. And so for a gem quality sample, the color of these different gems are basically defined by the different proportions of things like iron, magnesium, calcium, and manganese. And so almandine garnet, which is really common, has lots and lots of iron in it. Grossular garnet is super, super valuable because it's quite rare, and it has lots of calcium in it. It's mostly composed of calcium in this sort of part of the structural formula. Pyrope is magnesium rich. Spessartine, also very unusual, very beautiful as well, really unusual coloration, contains a lot of manganese. And these other two are sort of combinations of those other fews. And so I have quite a large collection of garnet jewelry. I think people think like, oh, she studies garnet, let's just get her some earrings or something. I don't know, which is very lovely and wonderful. But I am sometimes adorned with a lot of garnet things, which is quite hilarious to my colleagues and my friends. They think I'm obsessed, which I like to think that I'm not, but you might be able to judge slightly better by the end of this talk. But oops, yeah, so most people think that those natural gem quality specimens are sort of garnet as it is in the field. But in reality, this tends to be the sort of thing that we see when we see a rock and we think there might be garnet in it. So we've talked a little bit about these garnets as seeds. The poll that Bronwyn had at the start suggested that garnet got its name from pomegranate, which pomegranates have these little seeds, and garnet there is a sort of a dodecahedral or a soccer ball shape when you look at it under the microscope. And so you can kind of see this and you think, yeah, actually, I can see why it's called a seed mineral, because it looks like a load of seeds. It's like a load of poppy seeds in this rock. But I think a lot of people would say that this rock here is kind of less appealing than those gem quality specimens. But I think a petrologist, people like myself, would pick this rock over that gemmy garnet pretty much any day of the week, depending on if I needed some spare cash or something. But we generally go for something like this, and there are a ton of reasons for that. So firstly, this mineral garnet is pretty much everywhere. If you have a metamorphic rock that's formed by tons of different ways, you can get metamorphism, as we've talked about, as continents collide, but you can also get metamorphism during that subduction process that I touched upon. You can get metamorphism when you intrude this big igneous body and it heats the country rock around it. And so it's actually really, really common, and which means that it's kind of a really good comparative tool from one rock to the next. And also, and this is kind of related to the ubiquity of this mineral in a metamorphic rock, garnet is stable over a really wide range of pressure and temperature conditions. So temperature I showed you on the x-axis of that previous plot, and pressure being basically depth into the earth. And so anywhere from about 500 degrees centigrade, which is relatively low temperature for any kind of solid earth geologist, all the way up to the conditions at which the rock melts, for about 800 degrees centigrade. So it's really widespread, which means that people tend to use it a lot. It's really common to go to a conference and every single talk in the session somehow utilizes this mineral garnet in some way. And I'll talk about those ways in just a second. But I come to the field and I see this rock here. This is actually a picture from a rock in the Himalayas where I did my graduate study. I should have probably shown a more beautiful picture of like the mountain, but somehow I have pictures of rocks rather than the spectacular scenery quite often, which I think tells you what profession I'm in. But when I come across a rock like this in the field, I would prise a little bit off of it with my geological hammer, and I would take it back to the lab. And if the slide wants to move forward, perfect. So once we've collected that rock from an outcrop or sort of a surface exposure of this rock, we then use a big saw, diamond encrusted saw, to cut it apart. And we make something called a thin section, which is a 30 micron thick slice of rock, basically the thickness of a strand of hair, a couple strands of hair maybe. And we can then put that thin section underneath an optical light microscope, shine light through it, and look at the optical properties of the mineral in that thin section. And so this is an image of a thin section of a rock containing garnet. This is the garnet here, this sort of purpley taupe color. And so different minerals have different properties, so they look different. So this, like I said, is garnet. These sort of strandy bits are lots of micas. We might have some quartz or some feldspar plagioclase in these different regions. This brown is biotite, which is a slightly lower temperature metamorphic mineral, so will have formed before the garnet crystallized. And so when we look at these thin sections, we're essentially taking a section through that rock. So if you imagine we've got these little seeds, these little spherical crystals, and what you're looking at here is basically, if you imagine the garnet as a sphere, a slice through that plane. And so we're looking at this surface here when we look at this section of a grain. And so we can use our optical microscope and we can make all sorts of textural observations. We can look at the size and shape of these minerals. And then we can take that thin section, excuse me, to an electron microprobe, which basically fires a beam of electrons at the surface of that thin section. And we can use that to measure the chemistry in these different minerals. And so what we're looking at here is the magnesium distribution in that garnet that's in this thin section. We could measure things like iron and calcium and aluminium and various other elements as well. But really what you need to know is that when we have these bright red colors, we've got high concentrations, so lots of magnesium. And when we've got darker blues, we've got low concentrations of magnesium. And so what we say is that the chemistry of this mineral is zoned from core to rim. And so if you imagine a sphere, the core probably had to grow earlier in the crystal, and then it sort of grew outwards. And so the rim is the youngest. So we had some kind of change in the chemistry that this mineral was able to access during its growth. And so understanding this chemistry with an electron microprobe is really important, because the chemistry that's incorporated at any given time in a mineral is sensitive to the pressure and temperatures at which that mineral grows. And so, for example, a mineral that's grown at 450 degrees or 500 degrees will have a different composition chemically than that same mineral, say garnet, at 700 degrees. And so because we think we know something about thermodynamics and various, material properties, we can kind of use these different chemical and thermodynamic principles to predict the conditions at which this garnet might have grown, which is a fundamental principle and what a lot of people like myself do on a day-to-day basis. And so if that's not clear, if that's kind of just like kind of crazy, it's very conceptual, it's kind of a little bit hard to wrap your head around. Actually, a really good analogy for this kind of thing is a tree ring record. So we can look at a cross-section of a tree ring, and we can look at the width of different growth zones to tell whether it was a really, really good growing conditions, or was the climate good that year, or was it too wet, or was there a forest fire. We can kind of get an idea about the history of the growth of that tree and the conditions in which that tree grew, everything around it, from the earliest growth in the middle of the tree trunk all the way out to the latest growth at the rim of the tree trunk. And so in this case, the good thing about tree rings is that every year is really clearly marked. Maybe you've had a talk in this seminar series about dendrochronology, which is a really fascinating subject. And I think it's amazing because you can count, people sit and count literal tree rings and say, oh, this tree is X number of thousands of years old. Like, it's absolutely wild. But those dendrochronology records, these tree ring bands, make it quite easy to tell time. And even though a mineral is kind of zoned in a similar kind of way to our trees, it's actually quite difficult to tell time with a mineral, other than a relative time scale of older in the core and younger in the rim, because we have no sense of whether or not this mineral grew like that, or whether it grew over 1 million years, or whether it grew over 10 million years or 100 million years, because we don't have these clearly distinct markers of a given time period. So we need to have some way of telling geological time in the context of our garnet, if we're really going to try and use the chemistry that's contained within it to try and understand something about our Wilson cycle. And so that brings me on to thinking about geological time. You might have seen something similar to this before. This is basically the history of our planet Earth, represented as a 12-hour clock. So it formed at about 4.5 billion years ago here at midnight. And it's not until about 8 o'clock in the morning does complex multicellular life kick off. Is that right? Yeah, we get multicellular life, this pale blue line here. And then not until about 10:30 or 11 o'clock at night do the dinosaurs tend to kick in, which I don't know is their first vertebrates, so nearly dinosaurs. Complex vertebrate life kicks off at about 10:30, 11 o'clock in the morning, I suppose, before lunchtime, just before lunch, when everyone's starting to get hungry. And then we get humans in the last 2 minutes before lunchtime. I've already eaten my lunch by that point, so I've jumped the gun. But really, you know, as you'll probably all know, the history of our species on our planet is very, very brief compared to all of the geological time that exists, which means we have a ton of geological time to work with. And so if we want to tie the things that we're looking at, the minerals and the rocks that we're looking at, to some event or some age or some part of the evolution of our planet, we need to be able to tell if that rock formed here 100 million years ago or here 4 billion years ago. And that's really important for understanding how plate tectonics has evolved. Oops. And so we have several different ways of telling geological time. Firstly, we have something called the Law of Superposition, which is just a fancy way of saying that old things are at the bottom and young things are at the top. If you think about the Grand Canyon, all of the rocks that were basically sitting at the bottom of the valley right down by the Colorado River here, they were deposited over thousands of years as sort of sands and muds washed into that region. And as time goes on, more and more sediment builds up on top of it. And so the youngest rocks sit at the top. So basically the law of superposition says that anything that's above is younger, anything that's below is older. And so that's a really useful way of telling geological time. We also have the fossil record. If I have a fossil and we find out how old it is, the rocks around it must be of a pretty similar age. And then something in recent years is an approach called absolute geochronology. And so the most famous example of this is by using carbon dating, which we can use to extend the tree ring record. Well back in time, we can date organic material. And so famously, carbon dating was used to date the Shroud of Turin. And the fabric actually that is associated with the Shroud of Turin was actually found out to be 1,000 years younger than the supposed burial of Jesus. So that kind of put a spanner in some of these works and is one of the most famous applications of geochronology. But the principle of geochronology is the same for every kind of system. And this looks quite complicated, but hopefully we'll get through it. The principle of this approach is essentially that something called our parent, so carbon-14 or uranium in the case of nuclear decay, the parent decays to the daughter with some half-life, some set time, which means that if you start with 100 atoms of your parent, so 100 grains of your parent, say, in one half-life, and that half-life could be 1 year or it could be 1 billion years, you'll have 50% of the grains you started with. So if you started with 100 atoms and you had one half-life, you would end up with 50 atoms. If you then have another half-life, you end up with 25 atoms. And so you're progressively losing more and more of those grains as the parent decays to the daughter. And so if you know how much parent you have in the present day, and you know how much daughter you have in the present day in your mineral, for example, or your organic material in the case of carbon-14, you can measure them with very sensitive instruments, and you can say something about your half-life, and you can calculate an age. So you know how much time has passed since those elements were incorporated into our mineral in this case. And so in the case of garnet, we use this decay system called samarium and neodymium. And so 147 samarium, a lanthanide element far down on the periodic table, decays to a daughter of 143 neodymium with a half-life of 106 billion years, which means that it's really, really great for dating really old stuff. If you think about carbon-14, once you go through 4 half-lives, you've had about 20,000 years, which isn't very long, and you've only got about 6% of the original atoms left, which means it's quite hard to measure. So that's how different decay systems are able to date things of different ages. And so if we know how much samarium we've got in something, we know how much neodymium we've got in our garnet, we can determine an age. And so the way we do that with garnet is try and date different parts of that mineral. Again, this is just a tree ring record of a garnet where the core is older, in this case about 28 million years, and then we get younger and younger and younger as we go from the core out towards the rim, and we have a rim of about 20 million years. So we can progressively understand how a mineral like this evolved through geological time, and we had relatively slow growth in sort of these core regions, and all of a sudden the garnet ages start changing really rapidly. So we're adding much more of that mineral towards the exterior and the later stages of growth. before I move into talking about the Appalachians, do we have any questions popping up anywhere? I can't see the chat.
Justine asked about the Wilson cycle. I put another definition in, but we can go over that afterwards.
Okay, yeah, we can talk about that. We can talk about that in a little bit. So that was a lot of build up. And some of you probably have heard those sorts of words before, and maybe you haven't, which is also amazing. But I want to talk about the story that Baltimore garnets tell us in particular. And so this is a map, a satellite image of Eastern North America. And so on it, I've overlain a geological map of the Appalachians that run through here. And so what the Appalachians represent are a suture, basically the collisional point where an ancient ocean called the Iapetus Ocean closed. And so the ocean that was between two ancient continents of Laurentia and Gondwana closed. And so all of the blue in this map are where we have rocks that are associated with Laurentia, the core of ancient North America. And then on the other side, where we have these sort of browns and oranges and beiges, we have rocks that are interpreted to have formed on this other continent of Gondwana. And so basically, these rocks, these two continents have come together and they've sort of rucked up onto the surface, and we've got exposure of these rocks all along the Appalachians. And so I'm here over in Bristol in the United Kingdom, and actually that same geological feature runs all the way through Scotland, Ireland, and through Scotland. And I've not shown it here, but it also runs through, as we were talking at the start, through Scandinavia as well. And so there's a lot of talk about devolution here in the UK between Scotland and England. And Scotland and England have collided in the past and they've come together. So I'm hoping that we don't fall apart at some point in the future. But essentially, we've got the closure of an ocean running right through this region. And so the story isn't quite as simple as two things coming together, unfortunately. Things are always more complicated in reality. But as that ocean closes, we start to also collide things like volcanic islands and microcontinents that are sitting in those oceans. There's always islands kicking around, and they can collide progressively as well. And so we know that in the closure of the Iapetus Ocean, we had two different events called the Tectonic, when we had this island arc collide with continental North America, or Laurentia, at about 480 million years. And then a second event called the Acadian event at about 410 million years. And so both of these events happened before we had final closure of our ocean and the formation of Pangaea at about 310 million years ago. And so really the question is where did these different kinds of mountain building events occur in the Appalachians? How were they preserved in the rock record? And how quick did these processes happen? And so Baltimore sits right in the suture zone. And there's been a ton of study in sort of New Hampshire and New England. Everyone loves it up there. But it's really not very well constrained in the sort of central and southern parts of the Appalachians. We don't have a great understanding of this Wilson cycle in this region. And so this probably isn't news to any of you, but this is essentially what 300 million years of erosion will do to a mountain range. The Appalachians will originally have looked something like the Himalayas, and all of those high peaks have now been eroded down to the beautiful Appalachians that we all love and know quite well. And so I want to take us back to pre-COVID. I had just arrived in Baltimore. And so I had all these crazy plans to go to very exotic places and do field work. And all of that was curtailed, as we all know. And like I'm sure many people on this call were, we and my colleagues and I were all going slightly stir crazy on Zoom. So we hatched a plan to study rocks locally. And so this is a geological map of the Baltimore County area. And so these colors on this sort of satellite image here are exactly the same. You can see the same shapes, the colorations are different, but we have basically the same information overlaid here. So the 83 runs straight down through this region here. And so the red regions on this map are basically rocks that are the core of this ancient Laurentian crust, this ancient continent. All of these yellows are sedimentary rocks that are deposited at the margins of those sediments. We talked about this when we were thinking about the Wilson cycle. And from these different settings, we have sampled all over the Baltimore region. And so if anyone happens to go on this geology tour that Bronwyn was talking about in the start, you'll see many of the sites that we've probably sampled from, and you'll see some of the quarries and stuff that these building stones that you'll be looking at have been sampled from. But my interest is really in this yellow unit and these metamorphosed sediments. And so if anyone walks around Loch Raven Reservoir at any point, you'll see some of these kinds of rocks that I'll talk about. So we'll focus now on Overshot Run, a portion of the Loch Raven Reservoir, the northern edge of the Loch Raven Reservoir up here. And so this is what the site looks like. It's really highly vegetated. My little backpack is there for scale. I obviously went a few months before I left Baltimore and everything was in blossom and bloom. But this is kind of what rock looks like in the forest out here. It's really highly weathered. We've got the run coming up here. So you kind of have to traipse around to find it. But when you do find it and you zoom in on it, you see we have these really, really beautiful garnet schists. There's this other mineral called kyanite, which I won't talk too much about, but all of these purple things here are this really beautiful example of these little tiny little seed-like garnets. And so in this case, these grains are about 1 centimeter in diameter, slightly smaller in this case. These pens and ruler are here for scale. And so this is a really, really beautiful metamorphic rock. And this is actually a pretty normal metamorphic rock. It's really common around the world, doesn't make it any less beautiful, but it's a really typical composition and something you might expect to see in lots of metamorphic terrains. And so as you can see, I've highlighted where we find this rock in this picture in blue. So we're going to call this blue sample our fine-grained rock, our sort of rock A, our fine-grained sample. And anytime you see blue, I'm talking about this sort of finer-grained, beautiful garnet-bearing rock. If we go to other layers in this same region, what we see are what we affectionately know them as in the metamorphic community as monster garnets. And we have these grains that are multiple centimeters or a couple of inches in diameter. They're really, really big. You take them to any student and they're like, oh my gosh, these grains, these crystals are absolutely massive. This is wild. And these rocks with really, really coarse minerals are directly in contact with these fine-grained rocks that are really commonplace around Loch Raven. And that's kind of weird because these rocks are so close together. You think about, we talked about the law of superposition. The rocks in red here were deposited before. The rocks in blue were deposited immediately after that, but they've clearly got really different crystal sizes. So that's kind of weird because crystal sizes relate to either those pressures and temperatures that I've talked about before. If things get hotter, you tend to grow more, or they relate to the duration of mineral growth. So if something grows for longer, it gets bigger. And if something grows for less time, it grows for smaller. So it goes to a smaller size. But these two rocks right here, they're right next to each other. They should have seen the exact same metamorphic history during that collisional process. And so, oops, I'll go back here. So I'm going to touch upon how we try and answer what these different crystal sizes, you know, an obvious question is, why do these crystals, why are they so variable in size? And so, like I said, that could be related to the conditions at which the garnet grew and the duration at which the garnet grew. So related to the chemistry that I talked about before and the geochronology. And so to answer and try and address whether or not it was related to the conditions at which the garnets grew, we can, again, cut thin sections of these rocks. So this is these very thin 30 micron thick slices of rock, and this is the fine-grained one, and this is the monster garnet sample. And then we can take them to the electron microprobe, and don't worry about any of this stuff. I basically needed a slide filler. But basically what we find when we look at the chemistry of these rocks is that they actually formed at really similar temperatures, at about 600 degrees to 650 degrees centigrade, and 6 kilobars in pressure. And so that is equivalent to about 35 kilometers deep in the crust. So when these two rocks at Loch Raven formed, there was a 35-kilometer mountain sitting on top of it. And so they're not different in terms of their temperature. One wasn't really hot for some reason and grew bigger garnets. That's really unusual. It's kind of weird. And so the other question we want to try and use to discern why these grains are so different is whether or not one grew for much longer. And so I talked about geochronology before, this approach using samarium and neodymium, these two elements that concentrate in garnet. And so that's all well and good in practice, measuring these two masses, but actually both samarium, the parent, and neodymium, the daughter, the product, are in really, really low concentrations in a rock, 5 to 10 parts per million. So for every million parts, every million atoms, you only have 5 or 10 of each of these. And so to be able to actually measure them in a rock, we need to concentrate it and concentrate it and concentrate it and concentrate it. And so this is a process whereby you basically start with kilos and kilos of natural samples. So we went out to Loch Raven, we sampled the rocks there, and like I said, chopped them all up with our big diamond encrusted saw so that we were able to get through it. Then we basically try and find the biggest grains within this rock volume. Those biggest grains should have grown for longer, theoretically. And we can then basically slab and cut through the cores of those big crystals. So we try and get the core region, they're in here somewhere. We get the core regions of these big crystals that should have crystallized and grown at the earliest stage of metamorphism. We can then put these slabs underneath an electron microprobe or a laser to measure the concentration, in this case, of manganese. So again, this is another example of zoning where we've got high concentrations of manganese in yellows and decreasing concentration of manganese to the rim. And then this is basically our tree ring of garnet, early growth, late growth. And I want to date how the core, when the core grew and when the rim grew. And so to do that, we basically then take a dentist's drill and drill out along these little lines that you can see here, different zones of this garnet. So we've got a core, we've got a next outer layer, we've got a next outer layer, and then we've got the outermost rim region here. And so we end up with 4 chunks of this sort of 3 centimeter diameter garnet. We can then crush up that those little bits, and so we crush this up to like really tiny fragments, so we get this really pure sample. Each of these little tiny bits are about 75 microns, so less than 1/10 of a millimeter, so really tiny volumes of garnet. And then once we've done all of that, and that takes weeks and it's very boring, and you listen to a lot of music while you do it, and there's a lot of cleaning involved so you don't contaminate things. Then I went up to Boston for a couple of months, because this is then a long process, but you basically want to dissolve all of that garnet to basically isolate all the samarium and neodymium. You don't want anything else. And so to do that, you dissolve all of those different bits of rock and those different zones of your garnet in acids like hydrofluoric acid and nitric acid and hydrochloric acid. And there's a lot of pipetting and you go a little bit crazy. And so you're working in these ultra clean labs, and it was just post-COVID, and it was all this sort of crazy, takes 5 minutes to go into the building and 5 minutes to leave again. But eventually you dissolve all of your rock, you end up with just the samarium, which is in these orange little vials. You end up with just neodymium, which is in these green vials. And then you load up little tiny nanograms of material. You can't even see how much material it is. It's ridiculous. I still don't really understand it. But you pipette, you sort of suck up that little tiny volume and you put it on something called a filament here, and you heat it up so it gets rid of all the liquid, it evaporates. You load all of those little bits, different vials of samarium and neodymium on this barrel, and you put it in an instrument called a thermal ionization mass spectrometer, which is a very complicated basic piece of analytical equipment that allows us to measure very specifically and very precisely elements that are in really low abundance. Because even though we've gone through this month-long process of concentrating our masses, we still have barely any samarium and neodymium. We've gone from kilograms of material to nanograms of material to try and just isolate all of those parents and those daughters to accurately measure the ratio between them so we can effectively calculate an age. And so what do our results look like? Don't worry too much about these plots. These are figures known as Isoquon diagrams to my colleagues and I. And it's basically how we represent the dates that we calculate from this approach. And so essentially what you need to know is that the fine rock and the coarse rock, our blue and our red samples that I showed on that previous figure, have a really different age. The grains in the fine rock have a core age of about 390 million years, and the rim grew at about 380 million years ago. And so that means you had about 9 million years of mineral growth. Then you go just beneath it to that coarse rock, and the start of growth in the core was at 425 million years, and the rim was at 423 million years. So you grew these very, very large garnets almost instantaneously compared to slower growth of these much smaller grains, but they grew at really, really different times. They were separated by almost 40 million years. And so thinking about where we collected those rocks, that's super weird. You know, we think about the law of superposition and the fact that these rocks were deposited on the margin of our continent during oceanic spreading at about 1 billion years ago. They were then hit by one metamorphic event at 425 million years. We had one island arc collide with our continent, and it churned everything up and it metamorphosed our rocks here. 40 million years passed. That process happened again with some other piece of continent. Some of these rocks reacted, and some of them were overprinted by the later or the younger event, and others didn't. And this is very unusual. Colleagues of mine are like, what on earth is going on here? This is really strange, because if you think about the time scales that separates these two rocks, and you can go 1 inch and you've got a 425 million year old rock and a 380 million year old rock. And that time scale is basically the difference between not having any fish hadn't evolved when this rock gained its mineral assemblage, when the garnets in this rock formed. You go 40 million years later, fish have evolved. And so you've got massive geological time between the events that these record. And that's super, super confusing and a bit of a puzzle, and something we're still trying to work out. And so there's a really interesting story preserved in these Loch Raven garnets and these Loch Raven minerals. And so we've kind of whistle-stop tour again through the story that Baltimore garnets tell. It's really unclear why we have these differences in crystal sizes. Obviously, the big crystals are beautiful, the small crystals are beautiful, they're all beautiful, but understanding why some crystals grow big and some crystals grow small is really not a question you can easily answer. They also preserve 2 records of this 2 different metamorphic events, both at about 600 to 650 degrees, when we had closure of the Iapetus and collision of 2 island arcs during that period. But why does any of this matter? I kind of mentioned before, we know tons about the Northern Appalachians, but we really know almost nothing about the southern and central regions in terms of the relative timing of events in this region compared to in the north. And so, for example, this is just a sample here where some similar samples have been dated up in Vermont, and the age of that first collision, this Acadian event, is actually slightly younger. So it tells us something about how this island arc or this landmass, the angle at which it might have collided with ancient North America 380 million years ago or 390 million years ago, as is the case down in Maryland. And so it might be that these processes get older and they happen sooner down in the south, which is really important for understanding, you know, where we have these big suture zones and these collisional regions which concentrate metals and ores, and you have lots of fluid cycling. So it's really critical to try and understand exactly where and when these 2 continents came together. And then also we see in Baltimore this 425 million year old signature, and we have no idea what it relates to. And it's a massive puzzle. And if anyone has any ideas, that would be amazing, because I don't know, my colleagues don't know. It's right in between 2 things that we think we have a constraint on, but it's an as yet uncharacterized and unidentified thing in the Southern Appalachians. And so I've rabbited on for way too long, and that was very quick, but hopefully you've taken a few things away from that talk. Not least that rock metamorphism is really unique on our planet because of the modern style plate tectonics that we have. Garnet is the best of the metamorphic minerals in metamorphic rocks because they tell us about the temperatures that the rocks formed at. They tell us something about the pressures that they formed at deep in the continent. And they can also tell us something about the timing of the metamorphic events. And the story contained within these Baltimore rocks, and we've got another picture of some really beautiful Loch Raven ones again, is super, super interesting. And when you're on your walks in Baltimore County, please take a look out and sort of think about the sorts of things and the histories and the millions and millions of years of history that are contained within these sorts of samples. And so with that, I will be quiet and happy to clarify and chat and answer any questions you might have.
Thank you so much, Freya. And can you come back, stop share and come back together, and we can do questions together? That was an amazing presentation. I can't wait to go out to Loch Raven and look for these things. You know, a couple of people have said that they've already seen them, and so any questions, you can raise your hand, and then you can unmute, or you can put it in the chat box. Heidi did put in there, why don't the bigger crystals have grown? Why don't bigger crystals have grown slower? I think that may be something that we're taught, that the bigger crystals take a longer period of time.
Yeah, you would think that. Exactly. And that's something that I would have thought as well. If something's bigger, you think it's going to take longer. It's got more time to add new material to the surface of the grains. But it doesn't seem from our results, it seems like the big crystals grew very, very quickly, and the small crystals took much, much longer to grow much smaller, which means that maybe, for example, that the heat, so all of these grains need heat to grow. So you go up to 500 to 600 degrees centigrade. And maybe for this older event where we have these big granites growing at 425 million years ago, maybe you have a really rapid input of heat. You have loads of like advection and diffusion of heat around different bodies. And so you get rapid growth, whereas maybe in the smaller crystals, you know, the heat's kind of kicking around, you're colliding the crust, you're burying things are getting hotter slowly. You know, it's sort of a more sedate process, and it's kind of really poorly understood. And that was something that I'm really interested in, is understanding why rocks look the way they do, because we don't always have a good answer to that.
Yeah, Anita just says difference in pressure, or perhaps minerals in the solution as well.
Yeah, exactly. Crystal growth rate is going to be different. Minerals in solution. Yeah, and also I didn't touch upon this, but the composition of those two rocks is a little bit different. So the fine-grained rock has a lot of aluminium in it, which makes up that shiny mica that sits around the garnets. The other rock doesn't contain any of that. So it's not really clear how that would help it, but compositionally, there's something different going on as well. So there's a story of composition and time and all these different things that feed into that.
And Kathleen asked, does the temperature of the magma affect
the size of crystals? It does, yeah, it can do. It certainly can do. Also, the rate at which you're cooling. So if you're cooling very quickly versus if you're cooling slowly, that can affect the size of a crystal that will form. You know, if you're cooling more slowly, again, there's more time for things to attach to the surfaces, and you tend to get bigger crystals, which is why, for example, if you think about igneous rocks, not necessarily garnet, if you explode a volcanic rock at the surface and it's immediately ejected from a volcano, it forms a glass or a really fine-grained rock. Whereas if you have a magmatic body or lava that solidifies deep in the earth, the crystals have longer to grow. And so you get these coarse like granites and granites, for example.
Okay, a couple of things. One, Lauren asked earlier on a direct message to me, where do we find them in Loch Raven? They hike, you know, people, where should we be looking?
Yeah, so I'm always amazed anytime, I say anytime I go for a walk. When I used to go for a walk around Loch Raven, and I'm sad I'm not going to be doing that soon, really just look beneath your feet. So I'm looking at I won't share the slide again, but the geology underneath and around Loch Raven, all of it are similar rocks to these kinds of rocks. So you're going to see lots of garnet, you're going to see lots of mica. And so when you're walking around in the dirt, you often see all these glittery things, and that's all the mica. So just sort of get your face close to the rock if you can, and you'll probably see lots of garnets. The one that I've talked about is from a little run, Overshot Run, which is just to the north of Loch Raven, sort of a little offshoot. I think it's off Merrimond Road, if I remember correctly, without looking at a map. But you have to sort of do a little bit of a traverse through the woods. Better time is to go in the winter when there's less vegetation. It's a little easier to find. But yeah, if you just traipse around that area, you'll see plenty of them for sure.
I'm gonna put some people on the spot here. Maybe Martin or Tom or Al or Kathleen. We need to get together and do a little organize a hike out there so we can all go together and look for those. So I'm gonna be emailing y'all about going out there and looking for these together. Okay. All right. Let's see.
Yeah. Justine says
Nancy,
trails at Oregon Ridge has lots of the schist and garnet. Yeah, it's all through the Appalachians. They'll all tell a slightly different story. There's garnet all around the world.
Nancy has her hand up. So Nancy, you want to unmute and ask a question?
Hi, Nancy.
There we go. Oh,
Hey.
There we are. I'm a volunteer at Oregon Ridge.
Okay.
And we have trails with colors. There's a red trail and a blue trail. There's even a tan trail.
Okay.
And the tan trail is the best place to find. I think it's the best place to find garnets.
Okay. So
So
there's
it's
some
all
nice
trail.
examples along the
Yes.
trail, the tan trail.
Yes. Yeah, tan trail, named after Winnie Tan, who was in charge of Oregon Ridge for a few years.
Cool. I've never made it out to Oregon Ridge, but when I'm back in Maryland, I'm gonna have to pay a visit. Definitely.
It's close, very close to the lodge, to the nature center.
Oh, excellent. Yeah, I will definitely be paying both a visit.
Okay.
Thank you. And then Tom asks the depth. Tom Farrell asked, you gave the depths of the garnets formed at 35 kilometers. That's much higher than the Himalayas. Was there extra pressure due to tectonic collision?
Yeah, so the best way to think about that is, in the same way that a iceberg has most of its depth beneath the surface, mountains are kind of the same. So we don't think about them as, it's not sort of 35 or 20 miles from ground level. It's sort of 25 kilometers starting from somewhere beneath the ground. So it could be 15 miles down and then 5 miles of topography, or, so it's kind of a mass balance. It's a total. So it's not like we're at zero, we're at sea level, and then you've got 20 miles of mountain below. These rocks sit really deep in the crust as it is, because as you get continents collide, they don't sort of sit and just sort of go like that. They kind of all rock up and they get thicker, and the rocks go from the surface into the deep earth down there, and they've got a big, huge mountain sitting on top of them. That makes sense? Maybe?
Tom, does that answer your question?
And then do they
Nick,
rise up again? Because
Yeah. So the fact that we see these kinds of rocks is really spectacular when you think about, these rocks have been really deep down here and somehow they've gotten back up again. They will sometimes go through this process called exhumation, and sometimes that's along faults. So you have a rupture in the crust and things are brought up, or other collisional events come and sort of rock everything back up again. Sometimes in the case of something like the Appalachians, they used to be something akin to the Himalayas, and then you had erosion. And so if you imagine you had all these mountains and then you basically just chopped off the surface layer, you would then be looking into the ground level at that point after the erosion would basically be the core of the original mountain. So if you chopped off the Himalayas now, you would see at ground level really, really high pressure metamorphic rocks. And the process of erosion in the Appalachian has basically just cut in and removed all the stuff from the top, and it's just sort of sitting at the surface now.
Nick asks, I don't know if you can see that question, about the inverted topography in the Appalachians more than 20 years ago.
And this is current theory. And do you think the process of erosion goes between? Okay, I learned about the inverted topography in the Appalachians more than 20 years ago. Is this still current theory? I'm going to say no. Perhaps you could explain that to me. I've never heard of the expression inverted topography. So no, I was never taught it in my education, but that might not mean that it's not present theory, and it might just be a lack of my education and my understanding. And do you think the process of erosion could have collapsed the two zones together between the large and small crystals, making the timeline sequence? Yeah, so that is basically when we've got time missing. And so I've told you we've got time missing between these two layers, and you have sort of an unconformity or a gap between them. It's possible, but because in the picture I showed you before, and I actually didn't mention this, they look sort of folded continuously. And so they've kind of simultaneously been affected. It's really hard to say whether or not there was significant erosion. It's probably quite unlikely because that boundary is sort of continuous. There's no structures associated with it. It's kind of just a continuous, just progressive change. Like there's no evidence to suggest that there was any erosion through that region.
Okay. Jeff asks, is there a good reference for your final results? And I assume no results are final because we're still trying to figure out what it all means.
So yeah, this is hot off the press. I'm actually gonna, my colleagues and I are looking to submit it to a scientific journal in the next few weeks. So I can share the information and can share the slides and pass whatever information people are interested in along. I also have a website, which I probably should have shared. But if you Google me, all of the science that I do and the science that I put out is on my website as well. And so the Baltimore story will be there.
The Baltimore story, I love it. So Kathleen asks, so the contact isn't abrupt, could a different magma have intruded and then metamorphed?
Yeah, so that's an interesting question. Could a different magma have intruded? So I mentioned a second ago that these two different rocks are they have a different chemistry. If you measure the chemistry of the whole rock, they differ. So it might be that these really coarse-grained rocks are not a magma as such, but you have volcanic eruptions, undersea eruptions, for example, and they often they spew out various, we call them volcaniclastic sediments. So volcanic and clastic or sedimentary. So a mix of everything. And they get deposited on top of the muds that are sort of raining down from the continent as well. And so it could be that you had sort of a different kind of like little bit of everything else is sedimentary. And this is a little volcanic layer sitting between. And that might be the reason for this compositional difference that maybe has something to do with the grain size. But yeah, that's an interesting idea.
Martin just put in the chat box his map of the geology of Maryland. He is one of our curators as well in the geology department and wrote the Geology of Maryland book.
Oh, cool.
He has this wonderful resource. I recommend and suggest everybody get it and take a screenshot and put it in your
yeah, I've just opened it. Thanks, Martin. Great.
It's an ArcGIS online map.
Great.
And there's ways to add the quadrangle you have on the wall behind you to the map also.
Yeah, my new office here in Bristol is very sparse. I have some samples and a plan and a map of where are we? Towson? Yeah, we're in Towson up here. So there's Maryland is close to me every day.
Yeah, you have samples, so you brought pieces of Maryland with you, and literally.
Yeah, I think so, somewhere. Yeah, Overshot Run. Here we go, Overshot Run. So these are I should have had these out before. Interesting, some are missing. So yeah, so these are the little thin sections that we look at. So what we have is a thin bit of glass. So this is a picture that I showed you, that one of those images where we've got light shining through it, and you can kind of see all the different shades of gray in this case. When we shine light through that, polarized light through that, all of these different things are different minerals. So this is a garnet. This is a garnet. It doesn't look very impressive from here, but when you put it under a microscope, it looks pretty interesting. There's maybe a nice one. Oh no, it's not quite as nice, but kind of unimpressive. But when you look at it in different ways, there's so many things you can see.
You're holding billions of years in your hand right there.
Exactly. Yeah, exactly.
Heidi asked, do you visit garnet mines? And have you been to any in Adirondacks?
I have never been to a garnet mine, actually. I really want to go up to I think it's called Gore Mountain in New York State. And if anyone gets the opportunity to go to Gore Mountain, please do, because it's where you have the largest garnets in the world, and they're about a meter and a half diameter. They're absolutely massive. And so there's a lot of interesting science that's coming out about those as well.
I think that has another field trip opportunity for the system. I'll go into the garnet.
Go to the garnet mines. Because, I mean, and yeah, another interesting fact, and you probably know this, that garnet is really commonly used as abrasive because it's really hard.
I saw that when I was getting my icebreaker question, that's used, and it's been used in that capacity for a very long time.
Really? Okay, so like sandpaper and stuff, yeah.
Do we have any other questions for Dr. George this evening? Or she can go, remember, she's over there across the pond, so it's a different time.
That's all right. I'm awake now, it's good.
Yeah, she's never going to sleep now.
I'm never. I'll just stay at work. Actually, yeah, I've got early morning meetings, so I'll just stay. They're gonna think that I'm super dedicated and, make a good impression in my first few weeks. Oh, Fred has raised his hand. Go ahead, Fred.
Go, Fred.
Hi, and thanks a lot for your time and presenting. Wanted to ask. I think I understood you correctly. Just the formation of garnets in gneiss or gneiss is older material than the schist garnets. Is that true? Is that what I understood from your map that you showed, your graph?
Yeah, so you're talking about the plot where I had like temperature and depth? Correct. Yes, so gneiss is a funny word because geologists and petrologists define what a gneiss is very differently. We're quite a unregulated community, shall we say, because what some people call one rock, some people call something completely different, whereas things like igneous petrologists have very distinct classifications. But for me, so a gneiss tends to be something that forms after you have a schist. So at higher pressures and higher temperatures than a schist does. So when you have a gneiss, they tend to be, if you ever see like a really layered rock, and so you've got layers of dark and light minerals, that is usually a gneiss. So they tend to be really crystalline, whereas the rocks I've talked about have lots of these soft mica minerals in the sort of surrounding matrix. They're pretty, they're fissile, they fall apart quite easily. They're still relatively soft, even though they're hard rocks. Gneiss is a kind of another step up in the amount of metamorphism that they've seen. So they tend to form slightly later. You go from the sort of edge of a mountain belt into the real core of the mountain belt. So that's higher pressure and temperature again.
Right. Okay. Yeah. Because I've seen quite a lot of garnets in Maryland and predominantly in the schists, and did find one interesting location where there was gneiss or
Oh,
gneiss.
yeah. And you had
with-
garnets in them?
Yes, very gemmy
That's cool.
garnets. Very
Oh,
gemmy.
beautiful.
Yes,
Yeah,
they were quite gemmy. Some of the best I've ever found.
Wow. Okay,
Wow.
that's really cool. Yeah, there's some beautiful gneisses around Baltimore. Like, I mean, the Baltimore gneiss is an example. It's
Right,
everywhere
right.
in Baltimore. But yeah, that's great. You found it in that rock. It's not as common as in a schist.
True. And then these were dug up from laying down of a pipeline. So some of the rocks had been pulled up, and that's how come I was able to find them.
That's always good when you
yeah.
stumble across some building work.
Yeah, I mean, the fact that they were so gemmy and so pretty was very different than the schist ones, which tend to be opaque and iron, and a lot of they look rusty, if you will.
Yeah, definitely. Yeah, and I think some of that sort of if they're relatively fresh and they've been sort of dug up, it means that they've not been exposed to the elements for so long.
Sure.
They've not been so weathered. They're just a little bit more pristine as well.
So these would be older than, much older than the schist garnets, I guess, is what we're saying.
They could be, yeah. They might not be like, they might be like a few millions of years older. Not significantly, not like hundreds of millions of years, but in the same kind of ballpark. But yeah.
Do we have older rocks in Baltimore that contain garnets that you know about?
Do we have older rocks in Garnet? I don't think so. I think the rocks that I talked about today in Baltimore and Baltimore County area, and Maryland in general, I think these are probably the oldest ones. They're not the oldest rocks necessarily. Some igneous rocks are sort of 500 million years old, and so those erupt and form as sort of a different part of that subduction zone system. So when you get collision, you're getting rucking up of these sediments that I've talked about and metamorphism of them, but you also get eruption of volcanic lavas and magmas, and different parts, like different stages of the evolution of this collision produces different kinds of rocks. So yeah, there's some 500 million year old samples in Baltimore City. The Baltimore gneiss is an example of that. Actually, that's about right. That's about 500 million years old. So yeah, it is a bit older.
All right, Fred, we're gonna go to Bernie now. Bernie.
Yeah, I was going to ask this question before Fred. Have you noticed in other areas in New York, New Hampshire, or Virginia, wherever, the difference between the garnets like we have here in Loch Raven, which are non-gemmy, and highly fractured?
Yeah.
As opposed to gemmy garnets up around New York and everything else? Are they also in the schist, or are they in a gneiss up there?
Probably both. So I have a colleague actually who is up in Massachusetts, but he's from New York, and he, in a similar way to wanting to study the rocks that he knows and is around, he has a similar kind of study from basically Manhattan. So a lot of urban geology, we're trying to push a lot more of this sort of city geology. But he looks at rocks that are really, really similar to the rocks that we've seen here. We have the same thing, same kinds of sort of non-gemmy garnets and these schists up in New Hampshire as well. There are probably gemmy ones in the gneisses. I've not seen them, but probably scattered all through the Appalachians. There are certainly some down in Alabama, right in the southern tip of the Appalachians as well. And they're all sort of recording the same process, but at slightly different times, which is why it's sort of an interesting puzzle to look at different parts of the mountain range to try and be like, these are kind of the same, but they're kind of different. And why is that?
Yeah, because I guess these were formed 425 million years to 325 million years ago. The viscosity could have been different at depth when these were formed.
And definitely.
So the pressure actually caused the cracking of the garnets, not allowing the pressure wouldn't allow them to become gemmy, is what you're saying, basically.
Not necessarily. The gemminess has to do, as far as I understand it, with it's like the amount of inclusions. So it's like all the extra stuff. And so sometimes gneisses will be like an original igneous rock. So it's hard to describe it. It's like a little bit cleaner. Whereas you've got these sediments and they've got lots of junk in them basically. And the garnets grow over other stuff. And so it never produces quite as nice as a gemmy garnet from a gneiss, for example.
Well,
that doesn't make
yeah,
sense.
that pretty much answers my question, because I've had a debate with another gentleman here in Maryland who is convinced that all the garnets and the crystals in the Baltimore, Towson, and just actually in the Maryland area are all cracked and deformed because of the Blaustein asteroid that hit 35 years ago. And that puts it way out of the timeline of when they were formed.
Yeah, it probably
35 million years is too late.
Yeah, sometimes you do see evidence of shock. There's actually something called shock metamorphism. So I've talked about what we call regional metamorphism, where the whole region is metamorphosed because you've crunched up these continents. But you also get shock metamorphism when you have a massive impact. So that's a plausible theory, certainly, but I don't think it lines up with the times in this part of the world. So Marcia in the chat has said the Baltimore gneiss is about 1 billion years old, but garnet is not common in that gneiss, which I think is, which sounds about right. So the Baltimore gneiss is these big, actually, I can demonstrate on the map behind me, the Baltimore gneiss is in these cores of these domes. I can't go backwards. This sort of green area here, this green dome, and that's basically the core of an ancient continent. So that's that Laurentian continent, the billion-year-old continent that is sort of on one extreme side of our continental collision story. And so that's sort of, this is basically the same stuff that's most of North America is made of, and it's just popping up in this sort of collisional zone in Baltimore.
Thank you.
All right. Well, thank you so much for coming and spending your evening with us.
Thank you for having me.
Fabulous presentation. The next time you're over here, you need to let us know so we can show you around our collections, and then we can all go rock hounding together.
Definitely.
Yeah, so we appreciate everybody. Stay well, stay curious, stay outside, and we'll stay tuned, because we'll be going out together more and learning about the geology of this area that we call Maryland now. All right.
Thank you all for coming. Have a great evening.
Take care. Bye-bye.